Thank you. My name is Ahmed Bahjat. I'm here from George Mason University. Shout out to Jessica. Hi. I'll be talking about file fragments dating. You're probably first time hearing about dating on this forensics theme. So it's actually adopted from the archaeology field. They have two types of dating. They have relative dating and absolute dating, where you either pinpoint an age for an artifact, or absolute dating, where you put a timestamp on a date. So I'll be talking about this and our effort in George Mason to realize this. So the goal of our research basically is to put a timestamp on found artifacts on a hard drive, loose artifacts. So many often than not, you find deleted files that actually does not have any records on an MFT, or in which case you actually lost all the metadata, all the dates you have. And some of these dates are actually very rich. Some file systems, like the NTFS, store 8 dates for each file, 4 in the MFT record, on 4 in the file name record. And this will be lost if the MFT record itself is overwritten, which is very common. So there's a new field called digital stratigraphy. I think was proposed last year by Eugene Casey. In sync with our work, I started this like more than 2 years ago. And so the digital stratigraphy is basically studying the hard drive as layers, stratums, where the upper layer is always newer than the lower layer. The challenge here is this is not very obvious in many file systems. Some file systems are actually very random. You can't get any layers out of it. You'll see this when you compare NTFS file system versus a fat drive file systems. Also, another thing you might actually think about, I was a little bit intimidated when I was placed in the IoT segment, but I think my broader audience are actually in the IoT segment, because you guys are the ones who are finding these loose file fragments, either in a GPS GPS system, and I've seen actually this quite done a lot in research, where you have a TomTom GPS system, and you're trying to figure out when the guy actually visited that place, and you're trying to put a timestamp on a deleted log file in an embedded drive. So in these cases, this is your best fit. And actually, you're lucky enough, because most IoT systems use a fat drive probably, rather than NTFS. All right, so our approach is to use pretty much a reverse moving average of the neighboring files of a given sector, and we can pinpoint a probable date for our file. A little bit about the file systems. So in NTFS, we have 8 dates grouped into 4 dates in the MFT record, the typical MACB dates, and we have MACB also in the file name, record, I mean. And there's 2 types of overwriting a file in the hard drive. There is a content overwriting, and there is metadata overwriting. So you can either replace the pointer, the index in the MFT in the inode, or in the MFT index or MFT table, in which case you lose the metadata only, but still the file is in contact in the hard drive, which in many cases you can recover the entire file, and if it's something that you can deal with, you can actually get the dates, the internal dates from it, like a Windows Microsoft file, Microsoft document file, or PowerPoint slides, or a PDF file, where in many cases you'll find internal dates in these files, in which case you don't need our scheme to date these files. But in many other cases, the content itself is actually overwritten, and you have a pointer on the table. The last strange case, which happens also a lot, quite often, which is you have both cases happening in your evidence. You have partial deletion on the content, specifically in the header, the initial segments of the file, as well as the pointer to the file, in which case you're out of luck unless you try to date these files and get the probable date. File fragments can be found in either file slack. File slacks are getting bigger now. In the new file systems, the file slack is about 60. The file cluster is about 64 kilobytes, I believe, versus 4 kilobytes. And it can be resident files within the MFT, or it can be non-resident. It can be allocated or unallocated. So allocated means there's an overriding file on top of the file, generating the file slack where your fragment is found, or you can find your fragment in the unoccupied volume slack. All right, and our work does not address finding these fragments. We have, Jim Jones, my supervisor, is actually working on finding evidence for uninstalled softwares on a hard drive, in which case he uses MD5 hashing and partial hashing of files to find evidence of fragments. And then the following step is to put a date on these files. Of course, related work, we have, it can be grouped into time and forensics, reconstruction of events also related. File classification and recovery is also related. I want to skip those to get ahead. All right, so many anomalies. So this is a snapshot of a FAT drive. First experiment I did was trying to see the patterns of writing for a file. As you can see in the beginning, the files are sequential in the sector number until the hard drive is pretty much full. And we're reaching the last sector on the hard drive where it starts looking for empty clusters from the beginning of the hard drive. So this is called a next available versus first available scheme in the file allocation system. So this is a next available where it's actually sequential until you hit a broad block at the end of the file system. You start looking for empty clusters at the beginning. And it's not trivial work because you see a lot of anomalies. For example, the screenshot at the top it's bugging me for quite some time before I figured out this was an updated software. Because if you try to read these dates, you see the file at the beginning, it's in the same it's the same starting cluster number. The size has changed, but the dates are still the same for the accessed and created, but the modified is changed. So how can the file be changed while the access date still intact? And this is obvious for all of us because you can disable the update on the access dates for performance reasons. And also there's a lag on the access date caching. So it's cached for I think about an hour or so before it's getting overridden. So if you collect the hard drive before all the accessed files have been committed to the MFT, then you'll find anomalies like this. But this, I know for sure, this has been collected while after the file has been updated. So it was still bugging me until I realized that this is an updated software. So that they actually replaced the entire file from the internet with an updated modified date. So it has not been accessed within the file system, and it has not been, the created date is the same. Another anomaly in the lower screen on the lower side of the slides is you can see the file is actually moved in the hard drive. The cluster numbers change, but the dates are intact. It could be all the dates if you actually disable the last access date. But if you do enable the last access dates and you perform, for example, defragmentation, you'll see after a while, the date accessed has been changed. Another example as well, where you can see the date created also changed, and the cluster number is also changed because of a defragmentation. Another interesting thing is when you actually delete a file, none of the updates get updated unless you actually delete it to the recycled bin. In this case, you'll find evidence of the MFT records has changed, and the MFT record date will be changing. But then if you empty the recycled bin, none of the date will actually change. So it's still all the date. You cannot pinpoint a date where the file is moved from the recycled bin to unallocated space. So if you look at a typical hard drive, if we try to list the sequence of files in a timeline, we can call the files preoccupy the slacks before our fragment pre-file, and then post-file for the read one after the file. And you'll find evidence probably either through text searching or MD5 hashing, looking for a specific fragment, or you're looking for a binary string, for example, and you find that hit within another file occupying that slack. You know the upper boundary of your file is your file slack file system. So this slack owner, I call it here, the slack owner is the new file occupying this place where the file fragment is generated. So you can consider that as an upper bound. Of course, you have the natural upper bound of your or the files is the collection date or the acquisition date. So I mean, this is trivial. You should do this as a first calling criteria, where you exclude any files, any dates that happens after the acquisition, of course. And then you have a natural lower boundary, which is the file formatting date, so the date you actually create the volume. We narrow this down again as a slack owner date, so the slack owner is created after the file your fragment has been deleted, so that's a natural assumption as well. But the trick is, do I get the create date or the modified date of the slack owner versus the deletion of the previous artifacts? So we collected the data where our ground truth was snapshots of the M57 hard drives, for patch drives specifically. And we look into the files in each snapshot, trying to have a date, a set of files, a set of deleted files first, and we have the ground truth dates by looking into the snapshots, the day-to-day snapshots. So if the file is missing in the next snapshot, I'm assuming the file was deleted on that day. We actually try to optimize our deletion ground truth by looking into records from the USN journal. So if we do find an evidence of the actual deletion event from the USN journal, we update our ground truth to the date reflected in the USN journal. But as you can see also, if you dealt with the USN journal, it's not very very generous in terms of space to get overridden. So if you're doing a lot of deletion, you'll not find your data on the USN journal as well. All right, so we did our analysis for this data set. We tried to find the upper boundary and the lower boundary for each file, and then we calculated the residual error for our probable date of deletion versus the actual deletion date from either the USN journal or the delta between the snapshots. And we were able to actually get a pretty good shape at least for the upper bound, where at least 80% of the data were, we have an 80% accuracy for our data set on the upper bound prediction. And this is because we're dealing with the Slack owner, so the Slack owner files is mostly driving the upper bound, the upper bound deletion of the evidence file. The lower boundary is a little bit shaky because we're taking the moving average. You'll get a better shape if you're using the FAT system. It will be a lot more accurate. And actually, I have done that for FAT, and I've reached more than 98% accuracy and pinpointing to actual deletion date of the file with FAT. But with MFT, because of this best fit allocation scheme, you get a semi-random behavior on the writing pattern. So this is actually, this graph and the prior graph, the way you can read this is the accuracy giving your timeliness factor. So if you say, okay, how far are we with, if I need my deletion accuracy to be within, for example, 5 days, I don't care if it's actually more or less, then we actually reached 80% of accuracy. If your deadline is a little bit more loose, like 10 days or so, we can achieve more prediction. So most of 90% of our data fit on the 10 days period. But in the lower bound, you actually have to give me more time. So you have to give me plus or minus 10 days to get at least 80% accuracy. So in summary, this is an ongoing work, just in time, about dating file fragments, both in NTFS file system, which is this published paper, and the FAT file drive, which I'm assuming will be a lot easier, which we have done research on. But with this, you can at least have your evidence brought to court with a probable cause, because this is really critical. If you have an evidence without a date, it could be just useless. Thank you for your time, and if you have any questions.
Thanks, Ahmed. I really enjoyed that talk because it's interesting to see that an area of forensics that we think is very well established, that we're still finding and learning new things. I think that's great. I think we have time. Let's take maybe one question. Anyone? No questions. Okay. Thanks a lot, Ahmed.